very sophisticated. We're getting to be, we've got a lot of tools under our belt. We're going to talk about expectation of functions of random variables, okay? So let's let G be some function of random variables, x1, x2, up to, say, xn. So you've got n random quantities. They may or may not be independent. And G is some function of those random quantities, and you want to know how to compute the expected value of G of these random variables. And what it is well, if all these random variables are discrete, then it's just, guess what? It's a weighted average, right? You're summing up all of these things, G evaluated at all the possible X value combinations, but then weighted against the probability. This is the joint probability function. I should really probably have x1, x2, x3, xn down here in the subscript just to denote that it's the joint probability mass function for all these variables, but I don't have much room, and I think you understand what that is, right? This is the probability. This is just shorthand for the probability that x1 is little x1 and x2 is little x2 ... right? Xn is little xn. Okay. All right. If these random variables are continuous, then it's the same kind of thing, right? Except that you're integrating this function of the random variables against the joint density function for the random variables evaluated at these marks. Okay. And then with respect to each one of those variables. So you'd have the same number of integrals as you do variables if the x's are continuous. When is this useful? All the time. All the time. For example, let's say, Walmart has a hideous number of random variables that they have to deal with. Let's say x1 is the number of hammers and x2 is the number of swimming pools, and x3 is the number of screwdrivers, and x4 is the number of tubs of ice cream, and xn is the number of jugs of milk, etc. that they sell in a week, or maybe the demand for the random demands for those items. They might have a million different items, okay, and maybe G is actually this G function here is their profit. So their profit is going to be a function of this multivariate demand, right? Okay, and so they want to know the expected value of the profit, which is a function of all these random quantities, all these random demands in there. Okay, something like that. All right, here's an example for you. We've already worked with this joint density function, but let's take another look at it here, where the joint density function for x and y is 6/7 times x times y squared times the indicator of x being in 0 to 1 and y being between 1 and 2. Recall that x and y were found to be independent, right, by that theorem that we have. And just to remind you, remember, you want to be able to look at these joint density functions and see if you can partition them as products of functions, where one function is purely a function of one variable and the other function is purely a function of the other. So for example, here I've got 6/7 times x times the indicator that x is between 0 and 1, and then all that times y squared times the indicator that y is between 1 and 2. Okay, so in this case, yeah, sure, we can see that by the theorem that they're independent. This is a function purely of x, and this is a function purely of y. Okay, now maybe we're interested in x times y. In fact, what is the expected value of x times y? Who cares about that anyway? Well, let's see. What does x times y physically represent? here's what it could be. It may be that when we do this little experiment here that we're for some reason interested in the product of x times y. What is the product of x times y? Well, here's the origin. Here's the point 1, 0. Here's the point 0, 1. Here's the point 1, 1. Here's the point 0, 2. Here's the point 1, 2. Okay, those ordered pairs. Now note that our random point is going to fall somewhere in this square, right? The random point is going to fall in here. This is x, y falls in here. So then what is x times y? Well, let's say if that's our point, if it falls there, then x times y is going to be the area of this entire region. Okay? So x times y is going to be the area swept out below and to the left of this point, going all the way down to the origin. So it's the area of a random rectangle. Note that this point though could be down here, it could be here, in which case this would be the area. The random point has to be somewhere in this upper square. Okay, and so one thing I'm going to note right now, very quickly, is that that this expected value of x times y, this random area, should be somewhere between 0. Right, the smallest the area could be is if the point lands right here in this corner, then you've got the area of this little piece right here is 0 because its width is 0. Or the maximum it could be is if the point lands way up here, okay, then the area is 1 times 2. Okay, so my answer should be somewhere between 0 and 2. I'll just kind of check for that. But all right, so what is the expected value of x times y? That's what we want. Well, so we're told now that since x and y are continuous random variables, I need two integral signs, sorry. One equal sign, two integral signs. And I'm integrating the product, little x times little y, against the density function, the joint density function for x and y, dy dx. Okay. Why did I go dy dx and not dx dy? Well, because I wanted to. That's it. Okay. Which one you do first sort of depends on the physical shape. In this case, I have a rectangle. It doesn't really matter which way I go. Okay, so I'm going to do that, and let's see. So I'm just going to drop in my joint density function there, which is 6/7 times x times the indicator that x is in 0, 1 times y squared times the indicator function that y is an element of 1, 2. Closed interval 1, 2, dy dx. Okay. Now, since I'm integrating with respect to y first, I'm going to put all the stuff. I'm going to pull all the stuff that doesn't depend on y outside the first integral. Okay. So in fact, I'll pull the 6/7 all the way out. Okay. And I'll have 1x, 2 x's, right? I've got an x squared there. And I can pull that indicator function stuff out with the x in it, x in there, times the integral over the reals of y cubed times the indicator that y is between 1 and 2, dy dx. So really I've got this integral. Okay, and in fact you can see, hey, you know what, this is nice since they're independent, this dx, I can pull through. And effectively, I've got the product of two integrals here, right? All right, but let's just keep going here. I've got this integral x squared. 1 x is in, you know what? I don't need that indicator stuff there. I don't need no stinking indicator functions, right? Just go from 0 to 1 there. Times the integral 1 to 2 now of y cubed dy dx. There we go. That's all you need. 6/7, 0 to 1, x squared. This is going to be y to the 4th over 4. Whoops. Y to the 4th over 4 from 1 to 2, right? Dink, dink. Dx. Or this is 15 quarters, I think. Dx, right? We pull that 15 quarters out. I guess I get 90 over 28. 90 over 28. 6/15 is 90 over 28. Yep, that's right. So then I get x cubed over 3. 0 to 1. It's just a third of 90 over 28. This is 30 28ths, or 15 quarters, or 15 14ths. Yeah, 15 14ths. And yeah, indeed. Okay, so this expected value of the product does fall between 0 and 2. It does fall between 0 and 2, but it's not very intuitive that that this expected value should be exactly 15 14ths. Okay, we'll do another example here in just a minute. Sometimes these expectations are not intuitive, especially when you're talking about functions of random variables.